Whenever we talk about electron configurations or orbitals, we're referring to a series of concepts relating to the quantum mechanical model of the atom. And I'm actually going to start writing some notes here. The quantum mechanical model of the atom so the quantum mechanical model of the atom is basically a description of how electrons are organized in atoms. So the quantum mechanical model of the atom is a description of how electrons are organized in atoms. All right. Okay. According to the quantum mechanical model of the atom, an orbital, so an orbital is basically a field of space in which we know an electron exists, or could potentially exist. So in our understandings that we're writing down here, we're just going to write an orbital is a field of space in which we know, actually I guess in which, actually it's not just one electron, it's two electrons. So our revised statement here is an orbital is a field of space in which two electrons could potentially exist. All right? Now I know this kind of gets a little bit sketchy, but the idea of the orbital kind of goes back to something called the Heisenberg uncertainty principle, which is this idea that we can never know the exact position and velocity of an electron at any given time. And because of this fact, we can never really make a statement as to where an electron exactly is. We can only draw pictures of fields of space, three-dimensional fields of space, in which we know an electron might exist. And as it turns out, thanks to the Schrödinger equation, which would require differential calculus in order to understand, we basically were able to determine that every orbital which exists is basically a field of space in which two electrons could potentially exist, as I wrote here. Now, according to the quantum mechanical model of the atom, things are a little bit more complicated than just orbitals. You see, according to this model, all atoms contain energy levels. Right? And an energy level is simply, you can think of it as a three-dimensional distance away from the nucleus of an atom. Right? All atoms contain energy levels. All energy levels contain orbital clusters. Okay. Now, as it turns out, these two statements have some numerical properties which I didn't write down earlier. All atoms contain energy levels numbered. Now we give them numbers to sort of denote which one we're talking about at any given moment. As I was saying, all atoms contain energy levels numbered 1 to infinity. And this, if you don't know, this is simple for infinity. It's like a sideways 8. Okay? As it turns out, all energy levels actually contain orbital clusters with letters for names. Or I misspelled letters. Letters for names. Those letters are, or I guess those letter names are from smallest to largest, S, P, D, and F. Now, there are larger orbital clusters, and their names simply correspond to the rest of the letters in the alphabet. For example, G, H, I, and J. But in a typical chemistry class, we're never going to deal with orbitals this big. We're only going to focus on these 4 right here, S, P, D, F. If you want to remember a little mnemonic device, I just think Speedy F. Some of my annoying friends in high school used to say swag people don't forget. That sounds kind of dumb to me, but if that floats your boat, that's a very good mnemonic tactic. Okay, so we know that all energy levels contain orbital clusters with letters for names. Those letter names are, from smallest to largest, S, P, D, F, G, H, I, and J. Okay? Now, when we're talking about orbital clusters, we have to talk about how many orbitals exist in any given cluster with a specific letter for a name. So, we simply have to observe the following pattern. S clusters contain 1 orbital. Okay? P clusters contain 3 orbitals. Okay? D clusters contain 5 orbitals. Right? And F clusters contain 7 orbitals. And now from this point, if you wanted to go on to the higher order orbital clusters, you just keep counting up by 2. We could go 1, 3, 5, 7. G clusters might contain 9 orbitals. H clusters might contain 11 orbitals. I clusters might contain, I don't know, 13 orbitals or so. But we typically won't worry about that. Now, we know in our bigger diagram up here, all energy levels contain orbital clusters with letters for names. Continuing that little pattern in our notes here, all orbital clusters obviously contain orbitals. Okay? And going on this pattern here, the final piece of this four-part description of electrons is all orbitals contain from 1, actually no, not from 1, from 0 to 2 electrons per orbital. Now, with this new understanding that we have as to what orbitals are, we can sort of begin to appreciate what we're doing whenever we write an electron configuration. So, let's look at the chart that we drew earlier down here in a slightly new light. Okay, this will be a teaching moment. Let's draw a chart again. Number of electrons. And right here, let's write electron configuration. Now my camera is actually kind of in a bad position. I'm just going to refocus it real quick. Hopefully this won't cause too much disruption. Alright. Sorry if the silence is bothering you guys. I'm typically more talkative, but what I find is, in a subject like this, the less brain power I use in explaining a topic, the more easily people will understand when they watch the video. So that's why I'm basically not being as talkative and more focusing on just writing notes that express every part of the idea I'm trying to communicate to you that I myself already know. Because if you look at language, the purpose of language is to express thought, is basically to express ideas. I have this theory that all ideas originally start out as feelings, as intuition, and that's how we started developing these scientific theories about the world. We just had feelings as to what might be, and then we were able to fully formulate them into words. And that's basically what I'm doing up here. So, looking at our little chart from earlier, we remembered that if a given element contains one electron, I forgot configuration. I'll write the word configuration right here. Okay. If a given element contains one electron, its electron configuration is going to be 1s1. The one electron that exists in this atom exists in the s orbital cluster of the first energy level. Okay? If a given element contains two electrons, its electron configuration is going to be 1s2. Again, since we know that the first energy level of any given atom contains one orbital cluster, the s-type orbital cluster, and since we know that s-type orbital clusters contain one orbital, I should probably zoom out in my notes so you can see that I wrote that up there, just to let it sink in. Let's see. Yeah, I'll just do this. Since we know that s clusters contain one orbital, that one orbital can hold a maximum of 2 electrons, meaning the first energy level of any given atom can hold a maximum of 2 electrons. So, when we write the electron configuration of an atom with 3 electrons, its electron configuration must be 1s2, 2s1, because the first 2 electrons that we put into this atom both go into the first energy level's first orbital cluster, which contains one orbital, and therefore a maximum of 2 electrons in the first energy level. Meaning, the third electron of this hypothetical atom must go into that atom's second energy level. And I always like to say electrons are lazy. They're going to try to occupy the lowest possible energy orbital cluster. And what this means is they'll always go for the smallest orbital cluster in size that they can, meaning the one with the least number of orbitals in it. So we basically just go by our order here. Whenever an electron gets put into a new position in an atom, whenever we're imagining we're putting electrons into an atom, they're always going to go to the smallest orbital clusters first, fill those clusters up, then go to the next smallest, fill those clusters up, go to the next smallest, fill the cluster up, and go to the next smallest and then fill the cluster up until it either has to go to another energy level or goes to the next cluster. So when we write, I'm sorry, the light is really shiny. When a given atom has 4 electrons, its electron configuration is going to be 1s2, 2s2. Again, we know the s-type orbital cluster holds 1 orbital and therefore a maximum of 2 electrons. So, since we know that the second energy level contains 2 orbital clusters, actually I didn't write this up here in my notes, I apologize for that. But basically, I forgot to write this in my notes, I'm just going to write it out to the side. Oops. So I'm just going to write statements kind of like the ones I did up here. Energy levels contain the same number of orbital clusters sorry. Okay, energy levels contain the same number of orbital clusters as their number. And I know that's kind of vague writing the word number there. I couldn't think of anything else that would be more clear. But anyways, energy levels contain the same number of orbital clusters as their, I guess I should put energy level number. Okay, what this means is the first energy level, I guess I should say the 1 energy level, contains 1 cluster. The second energy level, or the 2 energy level, contains 2 clusters. The third energy level contains 3 clusters, and so on and so forth. Okay? So, since we know that the second energy level of this atom contains 2 orbital clusters, and since we know that this second level's s orbital cluster is already full, when we go to put an atom, or the electron configuration of an atom with 5 electrons, that next electron is going to need to occupy the next orbital cluster in the second energy level. So it's just going to go 1s2, 2s2, 2p1. And then we would basically just keep filling up this p orbital cluster until it reaches 6. And then obviously, since atoms are lazy, electrons are lazy, we're basically just going to keep going up until we reach 6, and then we're going to go up to the third energy level, in which case we would write like 1s2, 2s2, 2p6, 3s1, if that makes any sense. But anyways, just to sort of recap what we learned is the scientific definition of what an electron configuration is. The quantum mechanical model of the atom is a description of how electrons are organized in atoms. Okay? An orbital is a field of space in which 2 electrons could potentially exist. All atoms contain energy levels numbered from 1 to infinity. Energy levels contain the same number of orbital clusters as their energy level number, meaning the first energy level, or the 1 energy level, of an atom contains 1 cluster of orbitals. The second energy level of an atom contains 2 clusters of orbitals. The third energy level of an atom contains 3 clusters of orbitals, and so on and so forth. Okay? All energy levels contain orbital clusters with letters for names. Those letter names are, from smallest to largest, S, P, D, F, G, H, I, J, K, etc., etc. S clusters contain 1 orbital, right? P clusters contain 3 orbitals. D clusters contain 5 orbitals. F clusters contain 7 orbitals. All orbital clusters contain, I shouldn't have written the word orbitals here. I should have written, oh yeah, that's correct. All orbital clusters contain orbitals. That's correct. I'm sorry about that. And all orbitals contain from 0 to 2 electrons per orbital. Okay? So hopefully now you kind of have a better understanding of what electron configuration is. Now, spatially, an energy level is sort of a three-dimensional space that is occupied by orbitals. Think of it as almost a spheroid, if you will. A orbital is basically a space in which a hypothetical electron or two pair of electrons could exist. Now, if you want to actually see pictures of this, I'm not going to draw them here for you, but you can look in your chemistry textbook. But hopefully this helped you with this topic if you were struggling. And that's it. If you found this video helpful, please click the like button, and thanks for watching.